Hey contrarians, Millie Chainham here from the Decoding Crypto team.
Welcome back to another episode of Crypto in a Nutshell, the place where we unpack complex white papers without giving you a headache. Today, we're diving into a storage project that might sound a bit silly by name. It's called Walrus. But don't let that fool you. This isn't some meme coin trying to hitch a ride on animal branding. Walrus is a serious piece of infrastructure designed by the minds at Mysten Labs. And its mission? To fundamentally rethink how we store data across decentralized networks. Let's start with a problem. Blockchains are brilliant for coordination and consensus, but they're terrible at storing large amounts of data. Imagine trying to store an entire video, game, or AI model across hundreds of blockchain nodes. Every node has to hold a full copy, and that's just not sustainable. It's like asking every person in a town to carry a copy of the entire town library in their backpack. So naturally, dedicated decentralized storage networks started popping up. Systems like IPFS, Filecoin, and Arweave. They do a decent job, but they still have issues. Either too much data replication, high costs, or complex recovery mechanisms when nodes go offline. Walrus is a third approach. It combines the efficiency of advanced encoding with the smart coordination powers of a blockchain. At the heart of Walrus is a protocol called redstuff, a two-dimensional encoding method inspired by fountain codes. Sounds complex? Let me make it simpler. Imagine you've got a big file you want to store. Redstuff splits that file into lots of smaller pieces. Think of them like puzzle pieces. But it doesn't stop there. It arranges those pieces in a grid, then encodes each row and each column separately. The result? You've got multiple ways to recover the original data, even if some pieces go missing. It's like backing up a photo album in both horizontal and vertical stripes. Lose a few strips and you can still see the full picture. This dual encoding is what gives Walrus its edge. When a storage node goes offline, the system doesn't need to call up everyone else to rebuild the whole thing. It just asks a few other nodes for the missing strips, and boom, the data's back. That makes the network more efficient, scalable, and fault-tolerant. Now, how do you make sure nodes don't cheat, like pretending they're storing data when they're not? Walrus introduces a clever proof system. Instead of constantly checking every file, it challenges the nodes as a whole. The cost of proving you're storing data grows slowly, even if the number of files explodes. It's like spot-checking a warehouse, but being smart about which boxes to open. Let's pause for a second. If this is helping you make sense of how decentralized storage can evolve, do me a favor. Like this video, subscribe to the channel, and ring that little notification bell so you don't miss the next one. We're just getting warmed up. Okay. So, what role does the blockchain play in all this? Walrus doesn't reinvent the wheel. It uses SUI, a modern high-speed blockchain, as its control panel. All the coordination between users and storage nodes, from uploading files to registering proofs, happens on SUI. This offloads the data storage to specialized nodes while using the blockchain for integrity and coordination. When a user uploads a file, the system creates what's called a point of availability, a blockchain-verified signal that the file is now available across the network. If some nodes didn't get the memo, they simply recover the data from others. It's a graceful system designed for the chaos of real-world networks. Now let's talk incentives. Walrus introduces the WEL token, which powers the staking system. Nodes stake tokens to participate and earn rewards when they store data correctly or help recover missing pieces. Misbehave, and you get slashed. It's a classic carrot and stick, but optimized for long-term commitments. Nodes are encouraged to stick around, not just show up for a quick payday. Even better, users can delegate their tokens to trusted storage nodes. So if you're not running infrastructure but want to support the network and earn yield, you can back the nodes you believe in. The more reliable a node is, the more stake it attracts, and the more shards of data it gets to manage. Shards, by the way, are just chunks of the storage network assigned to each node. These shards can move around between nodes as the network evolves. Walrus has a robust system to handle these migrations, even when nodes leave or new ones join. And if a migration fails, the system recovers automatically, slashes the offending party, and continues on. There's even room for flexibility. Nodes can delete blobs under legal pressure or due to policy reasons by adding them to a deny list. As long as enough other nodes still store the data, it stays available. That way, censorship isn't enforced at the protocol level, but individual operators still have agency. So what does this all mean? Walrus is positioning itself to be the foundational layer for decentralized apps, digital provenance, encrypted AI datasets, and beyond. It's fast, efficient, fault-tolerant, and ready to scale. The team isn't just solving the "where do we store the data" problem, they're asking the bigger question: how do we store it in a way that's fair, resilient, and truly decentralized? And that's something worth paying attention to. So, contrarians, what should I break down next? Drop your suggestions in the comments. I've got my eyes on a few other storage protocols, but I want to hear what you're curious about. If you liked this breakdown, show some love by liking the video, subscribing to the channel, and sharing it with someone who still thinks decentralized storage means Google Drive on crypto. Until next time, I'm Millie Chainham, and this is Decoding Crypto TV. Stay sharp, stay skeptical, and stay decentralized.